Um, okay, well, thanks very much for coming along to my talk on navigating curves and surfaces in first-year calculus with physical models. And as you can see, I got the idea for this talk from the theme of today of our conference. I'm Poh Hillock from the School of Maths and Physics at the University of Queensland. And I'm really happy to be participating in Delta, and especially this year because it's held in my home institution. And in a lot of ways, this talk is only possible because it's held in my, the conference is held in my home institution, and you'll discover why. Okay, let's get stuck in. Are you familiar with the work of David Tall? He's very prolific. Well, he's a professor. David Tall is professor of, or was, sadly he passed away last year. He was a professor of math thinking at the University of Warwick. And he wrote this seminal book, How Humans Learn to Think Mathematically. And in this book, he talked about how mathematical thinking develops through the three worlds of maths. So there is the conceptual embodied world, which is based on physical experiences and perceptions. Then there is a symbolic operational world, which is based on symbols and procedures. And then there is a formal axiomatic world, which is based on definitions, theorems, proofs, deductions. So where does undergraduate maths largely take place in? Anyone? Sorry? Symbolic operational. I reckon that's kind of year 11, year 12, where they do a lot of, procedures. Formal, yeah. I think undergraduate maths largely takes place in the formal axiomatic world where proofs, definitions, theorems, deductions operate. But as you know, this world is very, very unsettling and disorienting for our first-year undergraduates. Why? Because the prior experiences are based mainly in the conceptual embodied world and the symbolic operational world. So there's a big gap between what we expect them to know at university and what experiences they come in with. So, the bridging that gap is requires a lot of deliberate and intentional support. So one way I have tried to do this in my teaching is, yes, I've introduced myself and we're ready to go. And it's through the use of visualization tools, all right, mainly either physical models or the use of software. And why? Because I believe visualization tools provide a cognitive scaffold to help my students move from the conceptual embodied world from the conceptual embodied world and the symbolic procedural operational world to the formal axiomatic world. Right. So, and this talk is mainly about physical models, and this is why I say it's ideal that the conference is held in my home institution, because I basically carted my whole office to the lecture theatre. Okay, anyway, let's get stuck in. I want to show you, so basically I'm showing you and showcasing some of the models that I have used in my course and which, according to my students, they have found effective. So let's move right on. Okay, my first example is this here. It's a board, wooden board. And with this wooden board, I put a piece of paper with two holes, right? I won't tell you what I'm doing. Maybe you will be able to guess as I go along. And then I have two pegs, and I put a peg here. Handmade models are by far the most fun for me. Two pegs there, like that. And then I have a fixed length of string, like this. So I'll do this so that our Zoomies can see. A fixed length of string. And then I need a pencil because I'm going to trace a curve, right? And this is how my curve is going to be traced. Right, you ready for this? You might have seen this before, okay? Somebody tell me, all right, maybe before you tell me, yeah, okay, it's an ellipse, right? Okay, it's a bit wonky there, but that's a model to trace an ellipse. And because we all know what about ellipses, what is the definition of an ellipse? It is the set of points, the geometrical definition is that it is a set of points on a plane, the sum of whose distances from two fixed points, F1 and F2, is a constant. And so this little snippet is taken out of our course workbook. And so we show our students this demonstration. And out of the geometrical definition, let me see if I can do this. Out of the geometrical definition, so I will place some coordinates here like this, the x and the y coordinate. This is y, this is x, this is F1, this is F2, and F2 has coordinates c, 0, F1 has coordinates minus c, 0. This is a point A, 0, this is a point 0b. Out of this geometrical definition, students can derive the algebraic definition of an ellipse, x squared over a squared plus y squared over b squared equals to 1. And in order to derive this algebraic definition, they need this relationship, which is c squared equals to a squared minus b squared, right? And this can be shown geometrically using this model. So that's my first example. Okay, now this one, I think, most people are familiar with this idea. But staying on the topic of ellipses, are you familiar with this idea of a Dandelin sphere? Who's heard of a Dandelin sphere? Okay, so how did I trace the ellipse? First of all, I fixed 2 points and then I trace the ellipse, right? I could turn the question the other way around, and I could say, if I give you an ellipse, how do we locate the focal points? So that's where Dandelin spheres come in. And okay, I'll show you what a Dandelin sphere is. This is a good time to show the model. That's a Dandelin sphere, tennis ball. That's a Dandelin sphere. Let me explain. Okay, so first of all, we have a cylindrical tube, right? And then what you do is you slice the cylindrical tube with a plane. It can be shown, and we set that as an exercise, that the intersection of the cylinder with the plane is an ellipse, right? So you see that orange plane there, the curve, there is an ellipse. And so what is a Dandelin sphere? You drop a ball that fits snugly in the sphere, into the cylindrical tube, and you drop it until it touches the elliptical plane. That point there, call it F1, and I hope you know why I call it F1. You do the same with a ball that fits snugly at the bottom, and then where it touches the elliptical plane, call the other point F2. And what are F1 and F2? They are the focal points. But the question is, why are they the focal points? And so, and that model there was made by my student, who introduced me to the beauty of Dandelin sphere. So you see, you can learn a lot from your students. And that's the Dandelin sphere that my student created. His name is Simon Jeffrey. And this picture here is really a picture proof for why F1 and F2 are the focal points of the ellipse. Okay, so it's got to do with the fact that F1 and F2 are the points of tangency, are the points where the Dandelin spheres touch the elliptical plane. So maybe if you stare hard enough at this picture, you can see why F1 and F2 are the focal points of the ellipse. Okay, right, so that's my second model. Okay, third one, I won't tell you what it is, but I'll tell you how we made it, how we made this model, and actually how my student made this model. It's made as follows. So can you read the details there? So the idea here is to get a ruler, fix 2 points on the plane, right? And then get a fixed length of string, right? The length of string has to be less than the length of the ruler. And then put a pencil there, and then keep the string taut as you move the ruler. And then you will trace a set of points. And guess what the set of points is? Want to play hangman?
Yes.
Yes, okay, give me some letters. A, yeah. P. Yeah, okay, I think you've got it. It's the trace of a hyperbola. And so why does it work? Because it can be shown that the distance between P and F2, the difference of the distance between P and F2 and P and F1 is a constant. It can be shown, and it's not difficult. And so we set this as a problem for our students, and it's not difficult to show with just about 3 lines of working that with this construction, this quantity is always fixed. Because what is a hyperbola? It is the trace of points on a plane, the difference of whose distances from 2 fixed focal points is a constant, right? So there you've got the picture, but I do want to show you the model that my student made. It's a little fiddly to show under the document camera, so I'm afraid the zoomies will have to miss out, but it looks like that. So you've got your 2 fixed focal points, you've got your ruler, and then you keep the ruler taut, you keep the string taut, and then you trace a curve this way. Can you see that? Yeah, a bit fiddly. So it took me a little while to trace the green curve. Okay, so this again was made by my student and very kindly donated to me. Okay, good, right. So ellipses and hyperbolas are examples of what we call conic sections because they are sections of a double cone. The other conic sections are circles, which are a special sort of ellipse, and the other one is parabola. So why are they called, as I said, why are they called conic sections? Because they are sections of a cone. So, what better way to show our students what these conic sections are? So here I have the bottom half of a double cone, right? And maybe I'll move this, put my next slide on. Okay, so if you no, don't tip the knife, just slice the double cone horizontally, you get your circle, yes? And then you tip the knife a little bit more, and you're going to get, if I can move this, your ellipse, right? Tip the knife a little bit more, and you get I think that's your parabola, right? And then you tip the knife a little bit more, and you get a hyperbola, well, one branch of the hyperbola. Right, so that again from our workbook, and so we show our students this so that they can see the idea of these conic sections as sections of a double cone. So one reason why we care about conic sections in multivariable calculus is that they give us a way of visualizing what we call quadric surfaces. So here is my next slide. Okay, these are the quadric surfaces we show our students, and they get a little unsettled because there are all these equations that they have to memorize and match with each one of these surfaces. But the idea is not to memorize these equations. The idea is to get them to see that when they fix one of these variables in each one of these equations, they are going to get a section or a cross section of the quadric surface. And how we help them visualize is again through physical models. So I've shown you mostly handmade models and a commercial model. And now I will show you some 3D printed models. So there you go. That's my ellipsoid, right? And these models have been made using STL files from Mathematica, just very readily, available on the net. So that's an ellipsoid, and hopefully by taking cross sections, you can show them that they get ellipses, and that should correspond with fixing X, Y, and Z to help them see that they are ellipses. And then there is the elliptical paraboloid, which is this one here, elliptical paraboloid. And then we've got the saddle, which is the hyperbolic paraboloid. So that's your saddle. And then you have the elliptical cone, which is this, that, like that. And then you've got the hyperboloid of one sheet, which is this one here, right? And then you've got the hyperboloid of two sheets, which look like that, like this. Okay, good. So far so good. I'm just watching the time because I'd really like to get on to my final model, which is made with a geometric construction kit. And this geometric construction kit is Zomi Tool. And I don't know if you've played with Zomi Tool before, have you? Well, here you go. So it's marketed as maths that you can feel. And here I have two very famous mathematicians and their Zomi Tool models. Do you know who they are? So, right, that's Conway. Penrose, that's correct, yeah. And Conway sadly has passed away, but Penrose is still around. He's 94 years old. So anyway, they obviously enjoy making Zomi Tool models. And so I want to show you my Zomi Tool model. It came out of this problem way back when I lectured calculus. We discussed this problem of optimization problem, where the problem gives you a picture of a honeycomb cell. And so the problem is you are given fixed S and H. And so the honeycomb cell looks like this. And maybe this is a good time to show you the model. So that's my Zomi Tool model. And it's a bit hard to see under there, but that's a Zomi Tool model of a honeycomb cell. So the opening of the honeycomb cell is a hexagon, and the rear is made up of three rhombuses that meet at a point. And so this S here is the length of the hexagon at the opening, and H here is, according to this diagram, the height there. There is a special angle called the trihedral angle, which is the angle between the height, the length H, and the one of each and the rhombus, each one of these rhombuses. So the idea here is to find that special angle theta, because bees like to conserve energy. So they want to build the honeycomb cells in such a way that they minimize the surface area for a fixed volume. So that's a problem. So luckily for my students, the formula for the surface area is given. And all they have to do is to derive this with respect to theta and find that optimal angle. So there's a nice story to this, which I have a few minutes to tell. So when I gave this lecture some years ago, a student at the back of the class at the end of the lecture came up to me and said, there is a problem with this question. There is a problem with the formula. And I was obviously skeptical. I mean, Stewart was on to its 6th edition, and surely an egregious error, and it was a rather egregious error, would have been picked up by then. And so there was only one thing to do, and that was to go back and check this question myself. And for somebody like me who finds 3D visualization challenging, that was the model that I made to check the formula for the surface area. So basically find, each one of these areas and then add up the areas of the 6 trapezium. And guess what? My student was right. There was a problem with the formula, but the problem was actually not with the formula. The problem was with the diagram, and I'll show you why in a while. So we wrote to the publisher, C&Gage. It wasn't rectified in the 7th edition. It wasn't rectified in the 8th edition. And the 9th edition, which has recently come out, has been, this problem has been rectified. So I'll show you the correct version and you tell me what is wrong with the problem. So this is the corrected version. This is the old diagram. This is a new diagram. The question is pretty much the same. Can you tell me the error? Yeah, it was a mislabeling of the H. H is not the height of that honeycomb cell. It is the length of the longer side of the trapezoidal wall. So with H correctly labeled, you can show that, and this was what I had to do in order to prove that my student was correct, that and it wasn't straightforward still, with a model. So there was still quite a bit to get through, that the formula is correct with the correct labeling. And so out of interest, do you know what this angle is? Theta? And when I tell you this, you will have one more special angle to remember that you won't forget. Everybody knows what arc cos √3/2 is, arc cos half is, but this one here turns out to be arc cos, 1/√3. The exact angle is 1/√3. And if you punch this into your calculator, it works out to approximately 55 degrees. So I've never forgotten what arc cos 1/√3 is, right? And it turns out the beautiful thing is that the empirical results bear this out, that the empirical results don't often differ from 55 degrees by more than 2 degrees, which I think is pretty remarkable and a wonderful way to tell our students how maths pops up, in nature. So, okay, so finishing up, I want to say that, okay, so as far as what my students thought goes, here are the comments, selection of the comments. And I haven't done any formal analysis. I haven't probed my students' understanding about how it helps them. And maybe somebody can tell me how to do that. But these are the comments from various course evaluations. And what I'm getting out of these comments is that the students are finding, well, they find it engaging, fun. It does make them sit up in class. And but more importantly, that it has helped the learning. And personally for me, I just find making these models and sharing them with my students very rewarding and very and a lot of fun. Makes teaching a lot of fun for me. So I will end on this note because we've got 5 minutes, I think, before the next talk. So just any questions you want to ask? Yes, Jess.
I love this. So thank you, Nicole. I'm teaching calculus 3, so multivariable calculus.
Oh, wonderful.
It's very procedural, the approach that I'm using because of our whole system. And I found that my students are really struggling with parameterization like this. And so I'm so curious if you've gotten to see either anecdotally or through any more formal, like how students who are learning about these surfaces in this way, when they get further on in their calc sequence, are they comfortable parameterizing these surfaces and integrating over them and working with them in a way that maybe my students are terrified of and not so comfortable?
Yeah, so I haven't done any sort of research into how students progress from this and how it helps their understanding later. I would say that when we teach parameterization, I carry this sort of thing into that topic. So I would show them lots of software where, when you vary t, they can see how the curve is plotted. So maybe not physical models, but software. Lots of visualization tools out there that can, teach student what parameterization means. And so as t changes, they can see how the points are plotted. So
yeah, so I have a question. So I'm online.
That of what these surfaces are and why the original formulas make any sense and why their parameterizations make any sense.
Yeah, well, that's exactly what I try to do with these surfaces. So when they fix x, right, they should see hyperbolas. When they fix z, they should see circles. And then when they fix y, they should also see hyperbolas. And that's how I get them to match the equations, because sometimes the equations only differ with the minus, the equations all look pretty much the same. Some of them have z, some of them have z squared, some of them have plus, and then some have a combination of plus and minuses. So by getting them to see these cross sections using these physical models, hopefully they can match the correct equation with the correct surface.
Well, your enjoyment of it is through too. And also you have a question online.
Oh, I do. Yes. Okay. That's all right. What is the question?
Yeah. So thank you for the opportunity. So when you're creating these models,
Thanks. Okay. So yes, you have a question, Ash B.
Can you hear me?
Would you like to unmute yourself and ask your question, or either put your question on the chat? 11:56. So that's, so
I am unmute
I'm
already.
unmuted. Oh, can we hear you?
I can hear you.
What's the reason for that? Okay, I think maybe you can hear me, but I can't hear you, and I think it's something to do with the way this thing's been set up. So would you like to key in your question on the chat box, in the chat box? Yes, Carlos?
Are these models also used in tutorials for workshops?
No, because we've got 30-something workshops, so I use them in lectures. But yeah, I think it'll be really nice to make a set for each, for each workshop.
I'm fine with their teammates.
Yeah.
They'll be ready.
Okay, did you make these models during the lecture time or not? Do you mean during the semester? Yes, no, I made these models outside of the semester. So a lot of these models were made in preparation for my lectures. Yes?
I really like how you introduced it with the anecdotal model, and I do clearly see that this links to the conceptual imagined world. But I do not quite see, and just to show my ignorance, how does this link to the formal and semantic world that you were hoping these students are entering?
Okay, right. So we don't actually get into a lot of this formal stuff in calculus. We're still basically at the symbolic operational world in the in calculus, in first year calculus, a multivariable calculus. So I don't know, I haven't really thought about how physical models would help them. And I guess that was really the point of my talk. I was trying to get them to move to the formal axiomatic world. But I guess what I'm thinking, and so an example that I'd be giving, which I haven't demonstrated here, is if you think about derivatives, I would show them in the conceptual embodied world, I would show them, a curve with a tangent line. And then after that, I will show them the symbols, dy, dx, and all the ones that Chantel was talking about, f dash and x dot. And then I will teach them chain rule, product rule, and so on. And then this then prepares them for the formal definition of a derivative, which is the limit as h approaches 0, fx plus h, take away fx. So I guess I'm not demonstrating that specifically with this model because we kind of stop here in our multivariable course. So I better, but thanks a lot for that. Okay, I think I better give this to Paul now. And Paul, you can set up while I